Okay, so we have been looking at how to evaluate limits based off of graphs and off of tables, and now we're going to get into how to do so algebraically. So first of all, we have all of these limit laws that we need to know exist so that we can evaluate them the way that we're going to. I'm not going to spend a ton of time going through these, but the basic idea is if you have like two functions added together and you want to do the limit as x approaches a of that sum, you can split that into the separate limits of each one of those functions and then add those things together. And the same is true for subtraction, multiplying by a constant, multiplication, division, all of that stuff still applies. So all of those need to be things that we can do so that we can simplify it and make it a little bit easier. So just know that those limit laws do exist and that technically that's what's going on behind the scenes. So we have some special limits here that we're going to need to know as well. If your function is just a constant, no matter what your x is approaching, the value of that will always just be whatever that constant is. If your function is just x, the limit as x approaches a will be a. And then if you have x to any power, it will simply just be a to that power. Or if you have the nth root of x, it will just be the nth root of a. Okay, so those are some special limits that you'll need to know as we evaluate limits. So the main part here is that we have this property called direct substitution. And if we are going to try to evaluate a limit algebraically, the first thing that we are always going to try is direct substitution. So what that means is that if I have the limit as x approaches a of some function, I'm simply just going to try to plug in a for all the x's in my function. And that will be the answer to your limit as long as that is a number that exists. Okay, so as long as it gives us it returns a number that is not an undefined value, that is going to be the answer to the limit. So an example of that, we have the limit as x approaches 5 of 2x squared minus 3x plus 4. The answer to this is simply going to be what I get when I plug in 5. And if you think about this, what we have is a polynomial. We should know that a polynomial has a domain of all real numbers. And so if I want to know what is the graph doing as my x's get close to 5, it's simply going to be approaching whatever my y value is at 5. Okay, so if I evaluate this, I have 50 minus 15 plus 4, which would be 39. Okay, so what that's telling me is with this, the graph of this function, 2x squared minus 3x plus 4, if my x's get really, really close to 5, my y values are getting really close to 39. Now, you can use direct substitution again as long as this is a defined number. If this is an undefined number, direct substitution does not work. So these next two examples, I'm going to give you a couple here where we can't just use direct substitution. And when we can't use direct substitution, what we're going to do is we're going to have to use some algebra techniques to help us simplify or rewrite the expression so that then I can use direct substitution. So I just want you to see what happens here. If I try using direct substitution on this first one, if I plug in 1, I get 1 squared minus 1 over 1 minus 1, which would give me 0 over 0. And that is a problem. Okay, I can't have 0 on bottom. It doesn't work. So I can't just use direct substitution here. So what I'm going to do is I'm going to use some algebra techniques again to help me with this. So I'm going to rewrite this as the limit as x approaches 1, and the top is something I can factor in this case. So I'm going to factor x squared minus 1 into x plus 1 times x minus 1. That's a difference of squares there. So factoring is a technique that you can use to help you. And the idea is, why could I not just plug in 1 because it made the bottom 0? But in factoring, I can now get rid of the problem. The problem was the x minus 1 on the bottom, which means this is the same as the limit as x approaches 1 of x plus 1. And now I can do direct substitution, which gives me 2. I want you to notice a couple things here. One, again, I can't just use direct substitution because I got 0 on the bottom. Two, I want you to notice that with every single step that I did, I wrote equals the limit as x approaches 1 equals the limit as x approaches 1 of, and I kept simplifying that. You cannot just take the expression and just simplify it out to the side and forget your limit part. Because if you're saying that the limit as x approaches 1 of that expression is equal to just a simplified version of that expression and not the limit as x approaches 1 of that simplified version of that expression, that is not mathematically accurate. Okay, so I'm going to want to see equals the limit as x approaches 1 carried along with the expression until, when did I stop writing that? Until I plug in 1 into my expression, and then I no longer have to write the limit. Okay, so the answer is just 2. I don't need to write the limit as x approaches 1 and then put 2. My answer is 2. I just had to carry that limit as x approaches 1 along until I got to that point. Okay, number 2. I hope that you can see that you're going to have a problem on number 2 as well. If you try to plug in 0 for x, you will get 0 on the bottom, which is not okay. So what we're going to have to do is simplify this expression as well. And what we're going to do here is not factor. We are going to multiply by the conjugate of the numerator. So anytime that you have a square root where you have stuff on the inside and stuff on the outside, you are going to want to multiply by the conjugate. I'm going to try to make that look a little nicer. You are going to want to multiply by the conjugate in order to simplify this. So we're going to multiply by the square root of x squared plus 9, and then instead of minus 3, plus 3. And I'm going to do that on top and on bottom. So the square root of x squared plus 9 plus 3. That's what I'm multiplying by. That is the conjugate. So I'm just changing that sign in front of the 3 there. Okay. Now, I haven't actually done anything, so I didn't need to rewrite the limit, but now I do. So equals the limit as x approaches 0. On top, when you multiply conjugates, you're really foiling this out. So I'm taking the square root of x squared plus 9 times the square root of x plus 9. Well, that's just going to give me x squared plus 9 because the square roots would cancel. Your outside is going to be 3 times that. Your inside is going to be negative 3 times that. So those two things will cancel each other out, and I don't need to write that, right? So 3 square root of x squared plus 9 minus 3 square root of x squared plus 9, those will cancel each other out. Remember, with conjugates, the middle two terms of that FOIL process will always cancel out, so you can kind of just ignore that. So I'm doing x squared, the square root of x squared plus 9 times the square root of x squared plus 9, which gives me x squared plus 9. Then I need to do the negative 3 times the positive 3, which would give me minus 9. Okay, I chose not to write the middle two terms because I know they're going to cancel. On bottom, I'm not actually going to multiply anything out. So I'm going to leave this as x squared times the square root of x plus 9 plus 3. Don't even distribute the x. So my advice here, always multiply out the parts that are conjugate. Never multiply out the parts that are not conjugate. So the denominator here, just leaving it as a product, not multiplying anything at all. And here's the reason why. My plus 9 and my minus 9 cancel each other out. And now the only thing I have on top is x squared, and that x squared will cancel with the x squared on the bottom. So now what I have is the limit as x approaches 0, and the only thing I have left on top is 1 now, because I've canceled that x squared. And then on bottom, I have the square root of x squared plus 9 plus 3. I got rid of the problem here, right? The problem was I couldn't plug in 0 to that x squared because it made the bottom 0, but now it's gone. Now I can do the direct substitution of plugging in the 0 for the x squared. So I'm going to stop writing the limit. I'm going to now just evaluate. If I plug in 0 in the inside of the square root, I get the square root of 9. So then I have 1 over the square root of 9 plus 3, which would be 1 over 3 plus 3, which would be 1/6. So again, what did we find here? We found that if we were to look at the function this square root of x squared plus 9 minus 3 all over x squared, and we graph that. As the x's approach 0, the y values are approaching a value of 1/6.